to talk about Chapter 4 and Chapter 5. Alright, so tonight we're going to talk a lot about Layer 2 security and in Chapter 4 and CBAC in Chapter 5. I'm going to actually try to get caught up by chapter, kind of dragging a little bit. There's not any practical application as far as GNS3 tonight, but what we will be doing is kind of setting the stage for a larger lecture on Tuesday with examples of a lot of GNS3. So I'm going to talk about Layer 2 security tonight, security features that are on switches, some things that you have to look out for in network design, dealing with spanning tree, port security, MAC address filters, etc. A lot of the security that I'm going to talk about switches from a design perspective is nothing necessarily that a bad guy or gal is going to do, a hacker is going to do, but it is one of those items where the network engineer messes up the network, or the network designer messes up the network because they either are ill-trained or uninformed, or let's just face it, just not dumb. So, securing Layer 2. In this chapter, we're going to cover the practices, the theory, principles of hardening a Layer 2 switch at the port level. Layer 2 switching is becoming faster and faster and faster all the time. Alright, when I started in this industry, 10 megabit Ethernet was blazing fast. Now it's like the slowest thing on the market. Right? We're getting into speeds of gigabit, 10 gigabit, 100 gigabit, 1,000 gigabit networks. Alright, most of the latter fiber optic. But it's getting that fast. Okay? And Layer 2 switching is very important to how we manage it and how we set it up for security. Because since those speeds are so fast, if an attack happens on a local area network, it can propagate at lightning speed. So the first thing that we want to look at is how Ethernet itself is set up and some of the inherent features of Ethernet and how we can combat them or how they can be used against us. The first thing we want to talk about is storm control. What storm control is the way that we manage or block broadcast storms. Broadcasts are all F destination frames in Ethernet. Okay, a MAC address is basically 12 characters in length. All right, either separated by colons every 2 characters or periods every 4 characters. The broadcast is all Fs. F, 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 F. That designates a broadcast. What a broadcast does, or what it tells the system to do, is I want this frame to go to every station on the network. So what storm control does is it can help manage or quelch broadcast traffic. Broadcast storms can be caused by malicious activity or just simple malfunctioning equipment. Okay, some network chipsets that were, are made by manufacturers like Emulex or Broadcom. If they break or if components wear out, they can just start pumping out all F signals and cause a broadcast. All right. combat this, the amount of broadcast traffic or time interval between the broadcast traffic can be configured. This is done with the following store and control commands. We're not going to go into that in too much depth. I wanted to bring that to light so you know that is a configuration feature on layer 2 switches. Protecting ports or private VLANing sometimes requires that not all traffic is sent between two hosts. You may isolate two hosts on the same VLAN with the use of protected ports. You must do this to both ports. Okay? So, for example, if I have a VLAN, right? Several PCs on that VLAN. For whatever reason, I have these two PCs. They can only talk to one another. I don't want to talk to anybody else. I can put that switch port protected on those two access ports, and only those two devices will talk to one another. Nobody else will talk to them. Okay? Now, private VLANs can also prevent inter-host communication. All right? Providing a certain level of port security. You can only try this on access ports. Do not do this on trunk ports. Okay? Real quick. There are two types of ports. On switches. So, say we have two switches. Real quick review. Let's say these are in VLAN 100, these are in VLAN 200. Let's say that these are in 100, these are in 200, and these are in 300. Okay? I have individual devices that are tied to them. PCs, printers, servers, whatever, right? Each one of these ports is an access port because it's tied to one single VLAN. Now, I need to tie both these switches together so that VLAN 200 can talk to VLAN 200, VLAN 100 can talk to VLAN 100. This is a trunk that I can configure multiple VLANs across it. I can configure multiple VLANs across it. If I don't configure this as a trunk, and these are both access ports, these ports take on the VLAN of what is configured on them. And only that VLAN. Okay? So setting up private VLANing comes into play, and it is very important when we talk about access ports across multiple switches. Okay?
Quick question, when you said there's two types of ports for switches, are you saying access ports and trunk ports?
Correct.
Okay.
Alright? You only want to do private VLANing on access ports. You can't do it on trunk ports. There are three types of VLAN ports: promiscuous, isolated, and community. So, let's say I have devices in, PCs in VLAN 200. Alright? And I only want these PCs in VLAN 200 to talk to one another. Alright? I only want this PC to talk to the router port. Okay? And I want this PC to talk to everybody. I can make these a community, this isolated, and this promiscuous. Depends on how you want to group things. Okay? Based on that security model, or that security premise. Okay? So if I only have These are the community, they're only going to talk to one another. If this is isolated and only needs to talk to its default gateway and nothing else, it's isolated. And this needs to talk to everybody, okay? It's promiscuous. Here's how you set that up.
I had another quick question for you on that last slide.
Sure.
You said isolated can only talk to the gateways, but on the slide at the last point you said it can also talk to the promiscuous.
It can also talk to the promiscuous, yes.
Okay.
All right. Gateway, yeah, isolated is only going to talk to promiscuous or its gateway. My fault. Hence why the promiscuous will be able to talk to everybody. So I've got to go over how that is set up in those next few slides. I'm going to skip over that. You can read that on your own. This is not going to be covered on the test of the lab, so I'm kind of, again, going to covering it because it is important, but I'm not going to go into it in depth. Port blocking. This feature blocks unwanted multicast and unicast traffic. Let's pause right there. What's unicast traffic? What's unicast traffic? I know you know, you sat in last class. One-to-one communication. Right? Host to host. Host to gateway. What's multicast traffic? Huh?
Is it sort of like how we talk to everyone?
Groups. So if I'm in a multicast group, I'm talking to everybody in that multicast group. It kind of works like broadcast, but in a more limited fashion. Okay? You can block multicast traffic and you can block unicast traffic by using the following commands. Be very careful with this one. You block unicast traffic, you're going to break stuff really fast. You would only use this if that end device is only and solely participating in a multicast group, nothing else. Port security. This is a very powerful and dynamic feature of iOS. It allows only a device with a registered MAC address to access that port. Now, this takes a lot of documentation, a lot of overhead, and a lot of patience to do, set up. Okay? And the reason you want to do this is to control the physical layer. So if you have a large organization, right, or if you have a community area, a high traffic area where people can plug in, you know, hotel lobby or a common area, all right, and wireless is kind of, we've gotten kind of away from this if we deploy wireless. But if you have certain MAC addresses that you tie to that port, only those MAC addresses are allowed to participate. Now, it doesn't stop me from trying to spoof a MAC address and guess. I can manipulate things that way, but it makes things harder. Okay? And the security MAC-add and then the source MAC address is how you configure that on a per basis. But it can be very administratively intensive because you have to keep tables and spreadsheets of MAC addresses, and it's for a small organization it's really good, really tight, but large organizations, no, it's a nightmare. A little bit more on port security, on how to configure it. And there's a couple of examples in Chapter 4. Now, access lists on switches use MAC level ACLs. I'm not going to spend a lot of time on this. They can be set up, and a lot of time while you set up a MAC access list is for access into the switched environment. Okay, now, you have to know every last MAC address. It's hard to put in MAC ranges because you're going to have different vendors, different manufacturers' equipment on your network, right? If you are solely using Cisco equipment, you can set up a MAC level access list only for Cisco's first set identifier of their MAC address. I really don't find that very much. Where I find MAC filters is on access points. Okay? On access points that are not controlled by wireless controllers. Okay? In small networks, home networks, works great. I have one at my house. I have 10, 12 devices in my home. Not that big of a deal. Not that big of a deal to administrate. So I was telling last class, I have one customer that when I started with Nick, their entire school district had an ACL-based access list on all of their access points. The lady administrating this, she spent the first 3 hours of her day, somebody needed access to the network, all she did was go in there and administrate ACLs. It's painful. Absolutely just really disorganized. I kind of scratched my head and wow, all I really have to do is spoof a MAC address and I'm on your network anyway. When I told her that, I think she was about ready to come home. Get around that. Put in a centralized control mechanism, a wireless controller. You can still do MAC filtering, but you can push it out to all the ACLs a lot quicker. And you can do a lot more on the security side of the house as well. Alright? Again, MAC-based ACLs, great for a small environment, does not scale well. That's your big takeaway. Spanning tree. Now, spanning tree uses BPDU, or Bridge Protocol Data Unit Guard. And this can disable a switch port from participating in spanning tree. Let's back up a second and talk about spanning tree here real quick. What does spanning tree do? What does spanning tree do, anybody?
To prevent looping in the switch.
What?
Prevent the looping in the switch.
Prevents loop at layer 2. Absolutely correct. Good job. So, I have a network. I have an MDF, main distribution frame, a few IDFs. What BPDU guard will do is, if I have other things going across here and I get really crazy with my network and I start linking things together. Alright, what spanning tree will do is it will work with BPDU guard and help block different links when they come up. Alright, spanning tree will do this by default, but BPDU guard will help you manage this better. So if I want to, say, block these two with BPDU guard so I can use this one as my default, I can allow myself to do that. Why? I don't know, but you can manipulate spanning tree in this fashion, okay, on an administrative basis. Alright, and in essence, the switch part will never go into the blocking state and will remain on constantly ignore spanning tree instructions to begin blocking. So it will pin up the connection. You have to be very, very, very careful with this, because if you don't use it right, you'll break your network. Okay? Root guard. Alright? What root guard will do is it will allow the election of a switch to be the root bridge, or set a root switch in spanning tree. Now, one of the things, let me back up real quick with BPDU guard. If you don't set this up correctly, alright, had a teacher at a middle school who thought he was Joe Engineer. He was, has no knowledge of networking. He thought that if I bring my own switch in and my own Ethernet cable and I plug in all these three, instead of having 100 megabit, I'll get 300 megabits of bandwidth. All he did was create a loop for himself, right? When this happens, you see CPU and memory utilization percentage spike up. Fortunately, in the school this happened at, we were monitoring it. I started getting alerts because he came in on a Saturday and thought he was going to be really, really, really cool and do all this and make it really faster for his students, and he basically brought the entire middle school down to his knees. Dispatched a tech out there on the next following Monday, found the problem, he found it in like 5 minutes, disconnected everything, brought everything back into alignment, if you will. And he spent more time explaining to this teacher why that was a bad idea than he did actually fixing the problem. That's all right. Oops, back up here. Root guard is where we control the election of your root bridge. Again, more administrative in nature, but from a security standpoint, it can help you defeat a denial of service attack. So a lot of times in a good architected collapsed backbone environment, you're going to have your core distribution and access layer network, or access layers. All right? Distribution, core, access. Right? In a Cisco environment, a perfect Cisco world, this will be a 6500 series switch, maybe a Nexus 7000. This will be a 4500 or a Nexus 5000. And these will typically be 35 or 3600s or Nexus 1000. Alright?
We don't have to know that.
Huh?
We don't have to know that.
No. I'll just give an example. The root guard piece is basically where you can go in and configure spanning tree guard root on each of these switches, and you can turn it off on them or default it to a low setting and a high setting on your core, and this becomes your root bridge. This controls spanning tree. It controls if you have additional links and mesh for redundancy, which is good. Right, which is good. It controls which ports are blocked, which ports become the root port, the designated port, etc. All right? Yeah. What root guard does? Okay, it will elect the root bridge, or it will allow you to set the root bridge, and then that root bridge, if you have multiple paths through the network, it will tell spanning tree, block this port, allow this port, use this port. It'll help you set your root ports, your designated ports on each individual switch. Okay? When you have a spanning tree topology change, that can become very processor intensive. Alright? Very processor intensive. So you want to have a higher level switch that's making that decision. Okay, 6500 in this case. Right? Now if you have another Cisco switch, because this is proprietary to Cisco, it comes in, or is it a Huawei switch, the Chinese company that makes, is it Huawei that they make switches? Yeah, that's based on Cisco iOS that was stolen. Alright? They can do that too. You have a lower end switch, say a 2940, and by whatever reason you don't have root guard set up correctly, or some way this gets elected as your root bridge, the topology change happens, this guy can't keep up. Case in point, I had an IT director from a municipality, decent sized municipality. Okay, not LA, but you know, a nice sized city. Call me, swore up and down he was getting hacked. Our city's under attack, our services are going out, we can't get out to the internet, you know, we can't have people talk from, you know, the fire stations to the city hall, to this, to that, the other. Help. Wow, that's pretty serious. So, grabbed one of my CCI securities, went out to this city, and started looking at their traffic and everything else, and right away, we knew it wasn't an attack. We just tell by looking at spanning tree. We saw all these topologies changes happening, and we know, okay, there's a loop somewhere. That was our first thought. You know, okay, so we practically went around to every last IDF in the entire city looking for a loop somewhere. Over the course of a weekend, we finally found a little 2940 switch at the new city pool, an IDF, that was configured as the root bridge for the entire city. Did that, everything came back. This thing was just like, its activity light was just solid green. All the traffic was going through that.
So for to do that, was that just default setting that was on that switch, or?
It was a switch that a consultant had put in, and he or she did not know what in the world they were doing at all. So again, sometimes it comes down to, if you don't know what you're doing, you need to research it, or ask for help, or call TAC, or something. Okay? Don't make assumptions. Assumptions bring down networks. Bringing down networks is bad. Bringing down networks will cost you your job. I can guarantee you that consultant never got asked back to that city. Ether channel guard is used to overcome configuration mismatches in spanning tree. Alright? So what ether channel guard is you can have multiple links between two switches. Alright? Like I had with that example where that teacher thought he was going to be really cool and get 300 megabits. You can do that. It's called ether channel. Okay? So let's say that I have 2 gigabit connections here. I can combine them in an ether channel and get a 2 gigabit connection. Absolutely. Okay? And I can make sure that that works with each of ether channel guard. Okay? To ensure that any type of misconfiguration between the 2 switches does not occur. And finally, loop guard. It helps prevent spanning tree loops by disabling the root ports, alternative ports, and alternative ports from becoming designated ports. Now, it's really important to understand that root ports, alright, and alternative ports, which is if a root port goes down, the alternative port becomes the root port. Alright, they control the flow of traffic, and a designated port is basically a port that is a designated port that you cannot block. It cannot go into blocking state. Okay? So if root ports and alternative ports become a designated port, you can have loops injected into your environment. Loop guard will prevent that. Let's talk about DHCP. The DHCP spoofing defense. Alright? This prevents rogue DHCP servers from entering the network for the purposes of gaining access. One of the ways that bad guys like to get into networks is if they can gain physical control, right? They may not be able to get a DHCP address. Or, even better, they can inject a DHCP server into the network so that your clients can get a DHCP address from them instead of somebody else. Or they can bridge the network in the case of a wireless network. I've seen this done before, where you do this. I have my laptop. I have my wireless card. I set up my wireless card as an AP. Right? I run DHCPD. Say in Linux. I then wire to the network. I can allow other laptops or wireless devices to connect to me instead of the normal AP, and I can hand them out DHCP addresses. Do a little bit of routing on the back end, and instead of them going through the AP to get onto the network, they go through my laptop. Now, why would I want to do that? Why would I want to do that? What did we do last class? What did I show you in GNS3? Wireshark. I can look at packets. And if I can sniff packets, what can I do? I can get all your information. Right? I can get all your information. Alright? You've got to be very, very, very leery of this from a wireless perspective. This is one of the reasons I never, ever, ever attach to a unguarded network, a non-secure network. I want to have encryption, even if it's web encryption. Like, at least I got something, right? Okay? This has happened on this campus. I've caught people doing this on this campus. Okay? I've caught my former students doing this on this campus. Anyway, DHCP snooping will help fight this because it won't allow DHCP to propagate the network unless it's from specific ports on specific switches. Yep.
In that scenario, has it totally, I guess, just disabled the original DHCP server so that it's not even aware that something else is giving out addresses? Or?
Right.
Okay. Is there something that, well, I guess if they've already got control and disabled it, I was going to say, is there a way that if they left it running, it would know that it didn't hand out an address that shouldn't talk to it?
Basically, once you cable up here, right? DHCP address, DHCP could happen through here, right? But with DHCP snooping, if I'm not coming from a specific IP address, I'm not going to allow it, okay? So even when these guys, now there is one other way you can get around this from a hacking perspective and fight DHCP snooping. That's if you put NAT on this thing. If you NAT and you have this completely isolated and is seen as coming from that, that's not going to work. Okay, so that, I think that's where you're driving with that.
Yeah.
So yeah, that won't work. Okay?
So for that means that laptop's RJ45 acting as a router.
Right. Okay. But if it's just acting as a bridge, all right? If it's just acting as a bridge, it will, the network will see this DHCP service and it'll crush it. So for every type of defense out there, you know, the bad guys and gals are looking for ways around it. Let's go into CBAC. Now, this is very important because this is a lot of what we're going to do in Lab 2. This is a lot of what we're going to do in Lab 2, especially with the iOS firewall feature set. And a little bit of what we're going to do in Lab 3 with IP inspect. So routers as firewalls. Yes, routers can be configured in a way to act as a firewall, a VPN appliance, and even as what we call a poor man's intrusion detection system. It has stateful packet inspection, which we're going to talk about here a little bit later, and that's a key piece of the lecture tonight. It will have context-based access control, intrusion prevention, and intrusion detection systems. An authentication proxy, which we're not going to go into too deeply. Port to application proxy, which again we're not going to go into too deeply. NAT and PAT, which we will talk about, and we're going to touch on zone-based policy firewall, which is nothing more than a virtual firewall or multiple routers within one router. VMware for routing, if you will. So the basic definition of a stateful firewall is that it is going to inspect traffic and keep the established states of connections up and running. All right, the key concept that I want you to grasp tonight is state. All right, after a TCP three-way handshake and access through a firewall happens, or outbound access through a firewall happens, that state is what we call established. And we'll go into that a little bit deeper here when we get into NAT and PAT. Okay, and that is one concept that you have to grasp because it's very important from a defensive posture standpoint. Okay? They can monitor traffic through syslog, okay, or through third-party application. It does network address translation as well as port address translation, which I'll go through here momentarily. Okay, and it's very important to understand how that works. But before we get into that, I want to talk a little bit about the method of attacks. The bad guys are not going to know what's on your network initially, so they have to do some form of reconnaissance. That is through port scans, ping sweeps. They got to find out what's on your network, what applications are open through different ports that you have open on your network. Then they can look at spoofing an IP address, doing a man-in-the-middle attack. They can look at what applications you are running, try to figure out what vulnerabilities are in that application, and even do denial-of-service attacks. Denial-of-service attacks, kind of old school, although they're making more and more and more of a comeback, especially with the LulzSec and anonymous groups, okay, the hacktivists that are out there. But the application level attacks are what worry me the most, okay? Denial-of-service attacks, not a whole lot I can do about it, okay, other than contact my ISP and try to filter that traffic upstream. This is nothing more than who has enough bandwidth or who has the bigger amount of bandwidth to overcome that. This is what you worry about. Because application level attacks are how hackers get into systems and gain information. Pull out personal identification information, account information, etc. Now, at the perimeter, your firewall is your key piece that blocks traffic. All right? And there are different types of things that you have to set up in a firewall. Okay, basic router security, which is what we did in Lab 1. Okay? We want to make sure that that device is nicely locked down from remote access, for example. It will do packet filtering. Packet filtering is basically set up to look at source, destination, address, source, destination, port, and protocol. Okay, we can filter based on that level of information. And then we have stateful inspection firewalls, which we're going to talk about tonight, the IP inspect feature. And here's where we need to get into understanding what state means. Let's take a very, very, very simple network, for example. PCs are .127 through, actually, .129 through 254. Right? And I have two servers, a web server, a mail server, and a DNS server, .8025 and 53 respectively. Okay, that's my network. Okay, stop. Okay, I need to get out on the internet. Well, in order to get out on the internet, I need to have some sort of public IP address, right? Right? So, my ISP gives me 202.101.18.0/20 block. Well, if I had a full Class C network, this wouldn't be a problem. What happened last year that was really, really, really bad? What happened with IPv4 address space?
Run down.
We ran out, right? Okay. Now, I can go to IPv6, no problem. Okay, not a lot of US-based companies are moving to IPv6. Okay, I hate to say this, we don't have a really good set of strong network engineers in this country, and Europe and Japan are kind of moving past us. But we can still get smaller blocks of addresses from our ISP. What we have to do is set up NAT or PAT. NAT is 1-for-1. PAT is many to 1. Okay? So for example, I want to give usually my servers, the things that I have services on, their own IP. Right? So I could put in a NAT statement in my firewall, for example, where 202.101.18.2 equals 192.168.0.80. That would be a static statement. Now, I have 1, 2, 3, 4, 5 PCs. 1, 2, 3, 4, 5, 6, 7, 8. Only got 6 public IP addresses. I'm using 1 on the outside of my router. I don't have enough IP addresses. Do these 3 get internet access and these 2 don't? That's not very practical. So I can use port address translation or a many-to-one scope where all these PCs translate through one IP address. For example, the IP address that's on the outside interface of my router. What the router will do is it will build a table so that 192.168.0.129 is going to get assigned a higher level port number, TCP port number. Okay? So that anything that goes out is tracked via a port number to its end connection. When traffic comes back, it knows which individual host to send it to. So when traffic goes out, gets established, okay, if it's TCP, if it's UDP you don't care, right? It's fire and forget, one way, who cares, right? But if it's TCP and it has to come back and make that handshake, all right, it'll track it within the NAT table, okay? In this same table, static entries are 1-for-1 as well, but we don't have to worry about it because they're 1-for-1, doesn't matter what traffic is. But PAT entries, you can have several PAT entries for several end destinations for one IP address. They'll just have a different port number each time. Okay? But once that traffic is gone through the network and we establish it, say we just go to Google and do Google search. Alright? That traffic, once it's outside the firewall and that handshake happens, that's called an established connection. Let's say we have a firewall rule set. Okay? We have to open up port 80 for outside vendors or the public to see our website. We have to open up TCP 25 for mail to come in, for mail service. We may have to open up TCP 53 for zone transfers on DNS. Okay? Now, regular UDP traffic, okay, just for lookups, that's fine. But to keep zone transfers and updates, we have to open up TCP 53. Anytime that has to come in from anywhere on the network, that's an established connection. Okay? Now, this is more controllable, because we can write access lists on the outside and point it and see it. We can really kind of shield, the